Today we want to take a look at even more double integrals. We've talked about how we build our double integrals. The big idea is that we have to describe the region over which we're integrating so that the integral can understand the values of x and the values of y we're plugging in. To that end, all we have to do is describe what x is between and what y is between, and that will, and we can plug them in turn. So we can integrate with respect to x, plug in the x's, integrate with respect to y, plug in the y's. We have talked about looking at a region and writing two double integrals to represent that region, one dx and one dy. Today, we want to look at that in reverse. I want to look at a double integral and figure out what the region looks like. And we're going to put some pressure on that by looking at this integral. So we have the integral from 0 to 1 of the integral from 3y to 3 of e to the x squared dx dy. So this is set up as a dx dy integral, which means that last integral are the y values. So we're integrating y equals 0 to y equals 1. So the dy is on the outside, so y equals 0 to y equals 1. That means the 3y to 3 is x. X equals 3y to x equals 3. This makes sense because that inside integral has y in it, and the inside integral, the early integrals, can only be functions of upcoming variables. We've only got 2 to choose from, so that first one must be x equals 3y. So it's pretty easy to see. Any questions? All right, so now we've run into our problem. If we want to integrate this function, the first thing we would do is integrate the e to the x squared dx. And now we have a problem. There is no nice antiderivative of e to the x squared. We can't do this integral as written. So we are stuck on this integral. We can't proceed with this integral as written because e to the x squared does not have a nice antiderivative. E to the x squared does not have a nice antiderivative. That means, by nice antiderivative, I mean finite combination of elementary functions. The integral of the antiderivative of e to the x squared either has to be constructed, or it is a non-elementary function, say with the second fundamental theorem of calculus, or we would need an infinite number of terms. So we're a little bit stuck because the first thing we have to do is e to the x squared dx, and we can't integrate. So our strategy here would be to look at this region, and instead of writing it as a dx dy integral, write it as a dy dx integral. Because if we integrate dy dx integral, the first thing we would do is integrate e to the x squared with respect to y. So that would be easy because e to the x squared is just constant with respect to y. Good question. Let's draw this region. So I'm going to draw the region where y goes from 0 to 1. Looks like my x's are going to be positive as well. Let me draw my region. So the y values go between 0 and 1. So that defines the top and the bottom of the box. the x is going to go from 3y, which looks like a line, to 3. So I got the left and right of my region as well. So my left is going to be the line, x equals 3y, and the right side is going to be x equals 3. So I'm just going to put this out here. That's where x equals 3. And now I got to draw the line x equals 3y, which means y equals 1/3 x, which conveniently connects the origin to the top left, top right corner of our rectangle. So if I draw the line x equals 3y, x equals 3y is my left bound, x equals 3 is the right bound. So you've got this triangle. This is the region that we're integrating over. Y goes from 0 to 1, and x starts off at 3y and goes up till 3. So that's the region that we're looking for. All we're doing is the same thing we did last couple of days in reverse. Instead of looking at the region and deciding left and right and top and bottom, we're looking at the integral and looking at top and bottom and left and right. Any questions? Is everybody okay? Of course, not going to be any questions today. We're walking into a 4-day weekend. I could do whatever I want today, and it could be confusing as shit, but no one would ask questions because you figure, I got 4 days to catch up. Of course, on Monday night, they're going to be turning TV on. It's like, oh, wow, that series Pam and Tommy was really funny. I don't think anybody would like it. You're all too young. You might not remember the mid-90s because you were like -10 when that came out or when that was happening. But still, Monday night, you're like, oh, wow, that was a great 4-day weekend. Then you're going to think, oh, shit, I didn't do any math work. I didn't catch up what I thought I was going to catch up on. You know what I mean? You ever tell yourself, man, I'm really going to get caught up this weekend? The first thing you need to realize when you find yourself saying, I'm going to catch up this weekend so I can go out tonight or play more Xbox or whatever that is, you need to know that that's a lie. That's the most important thing you learn about yourself. I don't care what you tell me. You can always lie to me. That's the nature of the teacher-student relationship. Oh, Leach, I'm so sick. I can't come to school today. Especially in pandemic times. Makes sense. I don't want you here if you're sick. But when you're sitting in front of your TV and you think, oh, I'll just catch up over the weekend, you're only lying to yourself. You know what I mean? So the reason that you're saying that I'll catch up this weekend is because you know it's a lie and you just want to keep doing whatever it is you're doing, which is probably not work. You know what I mean? If you don't know what I'm talking about, you're like, oh no, I actually do catch up on all my work. Then I'm not talking to you. I'm talking to the ones among you that have said that to yourself in the past, and it turned out to be not true. It's important to recognize that it's not true when you say it to yourself. You say, I better probably switch. But you have to just take care of that right now. Ask me how I know. I mean, seriously. So what we're going to do is we're going to switch the order of integration to a dy dx integral. So I want to set this up as a dy dx integral. So my x's are going to be my outer integral. And I'm going to change the order. I'm going to start with the y and finish with the dx. Now, in this case, when we're looking at a region and describing and writing an integral, always start with your constants. This, the dx is going to tell you the left and the right. The x's start off at x equals 0 and end at x equals 3. That last one has to be constant, so it's the first one you should fill in because you know it just has to be constants. Next, we can go on to the y. We'll pick a typical x value, figure out what is on the bottom and what's on the top. So if I pick a typical x value, the bottom is at y equals 0, and the top is at the line x equals 3y, which we'll have to turn around. So we pick a typical x value. What's the lowest y? What's the highest y? What's the bottom, then to the top? You just reverse the order of integration. Spend a couple of days finding out that these are going to give us the same value. And in this case, we have to switch the order of integration because we can't do that first integration. Now, when we go to integrate, we're looking at the integral of x squared dy. So e to the x squared is constant with respect to y. So now we can integrate. So now we can integrate e to the x squared dy because e to the x squared is constant with respect to y. You don't have to worry about this. It doesn't have a nice antiderivative business. Any questions? So let's integrate. The integral of e to the x squared dy is going to be y times e to the x squared. So this is going to be the integral. We still have this integral from 0 to 3, but the integral of e to the x squared dy is y e to the x squared evaluated from 0 to 1/3 x. We still have the dx, and we're still going from 0 to 3. So now we can plug in the endpoints. We're evaluating y from 0 to 1/3. E to the x squared is just a constant. So we get a 1/3 x e to the x squared minus 0 e to the x squared. But we still have to integrate this from 0 to 3 dx. So we did 1/3 x times e to the x squared minus 0 times e to the x squared. Questions? Now we have to integrate with respect to x, but look at how convenient this is. We get a 1/3 x e to the x squared. We can integrate that by substitution. So now we can integrate substitution. W will equal x squared. dw will be 2x dx, so we'll get a 1/2 dw is dx dx. Substitution. is w will equal x squared. dw will be 2x dx. And so we'll have a 1/2 dw is x dx. So our integral will be a 1/3 times a 1/2. So a 1/6 e to the x squared evaluated from 0 to 3. Then we just plug in the 3 and plug in the 0, and we'll get a 1/6 e to the 9th minus 1/6 e to the 0. Which would be 1/6 of e to the 9th minus 1. Now, if you watch this problem unfold and see us reverse the order of integration, do the simple integration e to the x squared with respect to y, and have that y install for us exactly the dw we needed, and you think that's awfully contrived. Like if we were a bunch of criminals and the guy says, this is how the plan's gonna work, and he's the new guy, you would all just get rid of that guy. Because clearly he's working against you, because this is just too good to be true. Along comes the y. Here's an x, so you do some substitution. What do you think? Too suspicious. Don't I know? Like in Scarface, that was the downfall of Scarface. Go, oh man, our banker isn't going to work. Well, I got a new guy. Isn't that convenient? Just as we lose the old guy, we get a new one. Seems too good to be true. You know what I mean? Especially for a guy as paranoid as Scarface was in that movie. Tony Montana should have seen this coming. Well, I've got a new guy, but I guess that just goes to show how coked up he was. Everybody seen that movie? I just realized that movie is probably like twice as old as y'all are. So it came out in like 1983. Fun fact, all the people playing Cubans in that movie, one of them was Cuban. That's it. For a popular movie, it sure does have a lot of like caricature. I mean, I know he's Al Pacino, but how far is Al Pacino as Tony Montana versus Mickey Rooney in Breakfast at Tiffany's? We look back at that and say, oh, that shit is offensive. How long is it going to be? Maybe it's now. I haven't seen the movie for a while. Maybe now, if we watch Scarface, we're like, holy shit, that's pretty offensive. What's wrong with you, Al? It's just rude. You know what I mean? What are we talking about? Oh, yes. That was too convenient because this problem is contrived. I don't think we need this kind of motivation to learn how to reverse the order of integration. It's a skill that we should be able to have. A skill that we should have. We should be able to look at an integral and be able to write it both ways. So another version of this, write the integral both ways. The other thing that I wanted to point out today in the double integrals category is when we have a function that's not invertible. The problems that this region is going to give us, bounded by the graph of 6x minus x squared and the x-axis. The problem that this region is going to give us is that 6x minus x squared is not an invertible function. Let's see why that's going to matter. This is going to happen at 0. This is going to happen at 6. And the top part is going to be 9. This is the example that I was going to do yesterday that I forgot to do, which is why triple integrals came up. Or a little bit out of order. The problem that we're going to see in this region is that the function 6x minus x squared is not invertible. One of the things we have to be able to do is rewrite y equals 6x minus x squared as x equals some function of y. But we're not going to get a function of y, we're going to get two functions of y. So here's our future problem in this problem. You need to see this kind of stuff coming. So the problem here is that y is a function of x, but x is not a function of y. Y is not invertible. But we still want to be able to write double integrals. So let's take a look at what we need to do. The easy way to make this happen is, since that function y equals 6x minus x squared is not invertible, I'm just going to use that as the top. I'm going to integrate y from 0 to at the bottom, to 6x minus x squared at the top. That means I need to do the dx integral on the outside and the dy integral on the inside. So when I set up a double integral, the easy direction is going to be dy dx. The easy direction is going to be dy dx. So setting up dy dx, I can just use x equals 0 to x equals 6 as my constants. There we are, left to right from 0 to 6. And then the y integral is from the bottom to the top. So the bottom of this is y equals 0. We're going to share. So for a typical x value, the bottom is going to be y equals 0, and the top will be the function. So we're not worried here. We set up a double integral. dy dx is the one that is going to be easiest because I can't invert y easily. Well, I can't invert it. It's not, or I can't invert it. It's not invertible. But that just means I can't write x as one function of y. I can write x as two functions of y, and those are the two functions that we're going to use. So let's invert 6x minus x squared. So 6x minus x squared is not invertible, but we can still solve for x. Now we could go through and try to use the quadratic formula. The quadratic formula for solving quadratic equations is trash, and we can delete that from our memory. Terrible way to go about solving quadratic equations. Use the quadratic formula. Because we know what this function looks like. 6x minus x squared is a parabola with a vertex at 3, 9 pointed down with a leading coefficient of -1. So I want to use that knowledge to help me solve this. This is a parabola. With vertex 3, 9 and lead coefficient -1. Because I want to write this in its vertex form. Because if I can set up an equation to solve where the variable I'm solving for only appears one time, I know my life has become much easier. So I'm going to rewrite 6x minus x squared. Leading coefficient is -1. The vertex is at 3, 9. Now we're going to have an easy time solving this equation because the x only appears once. So minus x minus 3 squared is equal to y minus 9. I'm going to flip that around. I want x minus 3 squared equal 9 minus y. And here's where we come up with the two functions, because we have to solve the square root, and that produces a plus or minus. So we get x minus 3 is plus or minus the square root of 9 minus y. So x is equal to 3 plus or minus the square root of 9 minus y. Two functions, 3 plus the square root and 3 minus the square root. I gotta stop leaning on the table. It makes the camera shake. It's like a Blair Witch project. Is it behind us? Oh no. I'm so scared right now. Me too. Shouldn't the batteries have run flat a long, long time ago? Quite. They weren't carrying enough batteries. Maybe able to get away with a lot of with fewer batteries or smaller batteries here in 2021, but when that movie came out now, batteries are gone there a long time ago. So wait, what are we talking about? Oh, yes. So now, when we look at our parabola, so when we look at this expression, 3 plus or minus the square root of 9 minus y, that 3 is a vertical line through the vertex. It's that 3 in the middle. Then we have plus on one side and the minus on the other side. That's using the symmetry of the parabola. It's the same distance. If we're at the same y value or the same vertical distance, we'll be the same distance away from the axis of symmetry. So here's the 3 in the middle. There's 3 in the middle. So that makes this x coordinate three plus the square root of 9 minus y. And on the other side, we have 3 minus the square root of 9 minus y. So the middle's at 3 plus the square root minus the square root. Now we can set up a double integral. Our original integral was set up as a dy dx, and so we want to set up a dx dy integral. When we're setting up integrals, we should start with the constants first. That's easiest. I spelled y wrong. So the y is going from 0 to 9. And the x will go from 3 minus the square root of 9 minus y to 3 plus the square root of 9 minus y. That's on the left. 3 minus the square root is on the left. 3 plus the square root is on the right. What made this problem tricky is that we couldn't easily solve for x. We had to do some stuff because we had to figure out what two functions we were dealing with. Fortunately for our heroes, we were given a parabola, and so we were able to rewrite it in the vertex form and use that to write our two functions. Any questions? Comments? All too easy? Told you, Calc 3 is a breeze. Calc 1 and Calc 2, your first learning stuff, you only get to use one variable. Yeesh. Terrible. Calc 3, no problem. All the same stuff. One of these double integrals is probably better to work with than the other. The previous one that plugs polynomials into our antiderivative dy. This one is plugging square roots in our antiderivative dx. We generally like to avoid getting square roots when they're more than before.
How's everybody okay? Everybody looks so very sad. Because I just spoil everything and don't make you solve for it yourself. No one likes that either. So. All right, so that's what we want to think about with double integral. What's x between from left to right? What's y between from bottom to top? The last one has to be constants. The ones in the middle can be functions. Pretty much always start with your constants, whether you're looking at a double integral and drawing the region, or looking at a region and writing a couple of double integrals. Start with your constants and then draw a line between the top and bottom or the left and right. All right, that's going to do it for today. That's going to do it for this week. Everybody have a nice 4-day weekend. I'll see y'all on Tuesday. Thank you.